is the second appointment of the ReStructure 2.0 webinar series. I will give you just a summary of the project for the people that are not aware of this. First of all, I will give you what is ReStructure 2.0. ReStructure 2.0 is a research project based at the Department of Civil Engineering of the University of Calabria that was funded by the European Commission to the Marie Sklodowska reaction in their integration panel, and I am the PI of this project. This webinar series was the scope of the project of this webinar series is to create an active network in which discuss about topics from the broad area of the geotechnical earthquake engineering, and of course to disseminate some research. For this reason, we will have one appointment more or less every month. There will be some summary, interruption, error, stuff like that. And then we will have these online webinar, but soon there will be also some in-person webinars, but the online connection will always be available. The presenters will be worldwide experts in the broader area of geotechnical earthquake engineering, and this is the list of the confirmed speaker. And today we will have the first host, that is sorry. Can you see my the slide?
No, we just see just you.
Me talking. Okay, that's okay. And now I guess you can see.
Yeah, we see it
my
now.
slide. Okay. So I was just saying that we have several national, international experts. The confirmed speaker today, we have the first guest, that is Professor Scott Brandenberg from the University of California, Los Angeles. And to be informed about the ReStructure 2.0 webinar series, you can subscribe to the newsletter through the website, or just follow the pages of ReStructure 2.0 on social media. We have a Facebook, Twitter, and Instagram account. So let's start with the first seminar, that is presented by Professor Brandenberg. Professor Brandenberg is a full professor in the Department of Civil and Environmental Engineering at University of California, Los Angeles. His research focuses mainly in the broader area of geotechnical earthquake engineering, with focus on soil structure interaction, multi-hazard reliability of levee system, the response of deep foundation to liquefaction-induced lateral spreading, seismic earth pressure, active earth retaining structures, and cyber infrastructure projects. He was awarded with many different awards during his career. Among others, we can mention the Huber Award in 2015, the Prakash Research Award in 2013, and the Arthur Casagrande Award in 2010. I know Scott since 2016, when I started spending a few months in the US, and then have been honored to be his postdoc for a couple of years at UCLA. And then after that period, we are still collaborating, and we are doing some very interesting research. And of course, for me, it's an honor to have him here. And so, and I can assure you that it's really a joy working with him. So please, I give you the floor, Scott. So I will stop sharing. You can share now your screen. And thank you again for being here.
All right, great. Thank you, Margot. Let's see. Okay, so you should be able to see my slides, right?
Yes, we can see
Okay,
that.
great. Well, first, Margot, congratulations on your prestigious fellowship. I think it's wonderful that you received it. We miss you here in Los Angeles, but it's great to keep in touch through these sorts of webinars and to continue working together. And thanks to all of my European colleagues for coming today, and good afternoon to all of you. So my topic for today is going to be some research that we conducted here at UCLA and at the centrifuge facility at UC Davis during the past 5 or 6 years or so, to look at the influence of soil structure interaction on ground failure. So typically in SSI, we're worried about how is the ground going to influence the performance of the structure. in this presentation, I'm kind of flipping that upside down and saying, how is the presence of the structure going to interact with the ground and potentially contribute to failure in the form of things like liquefaction of sand-like soil or cyclic softening of clay-like soil. So my collaborators in this work are Jason Binker, shown there on the left. He was a PhD student here at UCLA until just a few years ago when he completed his PhD and moved on to a position at Shannon and Wilson in Chicago. If anyone asks me a really hard question, I might just have to refer it to Jason. And then Jonathan Stewart, who I suppose will be giving the next presentation as part of this series, my colleague and professor in civil and environmental engineering at UCLA. So the outline today, I'm going to talk just very briefly about some of the field observations of cases where we've observed ground failure beneath structures and maybe not in the free field. So there's some evidence that soil structure interaction played a role in the ground failure and the poor structural performance that we've observed. Then I'll also really briefly cover some recent methodologies for computing structural settlements due to SSI. It turns out that we, as a field, have largely ignored soil structure interaction when we do our liquefaction evaluation or ground failure analysis. And that is changing. There's some new procedures that are fairly simple and straightforward to implement that allow us to now compute structural settlements, whereas before maybe we were just doing a free field settlement analysis due to volumetric strain of the soil. And then I'll talk a little bit about the motivation for why we need the work that I'm presenting today. And that work is a new theoretical approach for incorporating SSI into ground failure analysis. And this is basically an extension of the current procedures for assessing liquefaction triggering or cyclic softening for free field level ground conditions, but one that incorporates stresses from a vibrating structure. So I'll talk first about an invariant-based cyclic stress ratio. Stress paths that are exerted on the soil beneath vibrating structures are more complicated than the simple shear stress paths that we analyze for free field cases. So we need to do some work to come up with a more robust definition of cyclic stress ratio that can accommodate those more complicated stress paths. Then I'll talk a little bit about corrections to resistance for path and static shear stress. There's also magnitude scaling factors. So some of these things are different when we have soil structure interaction and when we move to an invariant-based analysis framework instead of just looking at shear stresses on horizontal and vertical planes. I'll then talk about the centrifuge modeling program that Jason conducted at UC Davis. He spent a good chunk of time during his PhD at UCLA living up in Davis, building these centrifuge models. And so I'll talk briefly about their configuration and some of the observations that we made. And then I'll show predictions of those observations using this new method for ground failure analysis we're proposing before I wrap up. And I will say, as kind of a preview, in the centrifuge modeling program that Jason conducted, we did get significant settlements and even a bearing capacity failure of one of our structures that tipped over, and it was resting on a low plasticity clay that is susceptible to cyclic softening. All right, so on to a brief overview of some field observations. This is a very famous image from the 1964 Niigata earthquake showing the Kawagishi-cho apartments that tilted to varying degrees depending on the type of foundation as a result of soil liquefaction. Now this one is not maybe as clear about whether SSI played a role in the ground failure because there was liquefaction all through this whole region, including in the free field. And so it could just be that we could do a traditional liquefaction triggering evaluation and say, yeah, this soil is going to liquefy, so these structures may have settlement or tilt as a result, without really even incorporating SSI effects in any kind of robust framework. But then there are other cases that are not so clear as to whether a free field kind of analysis would allow us to predict ground shaking. Let me hide that little thing. This is one from the 1999 Chichi earthquake, where there was these sort of punching failures of spread footings into a clayey soil underneath, and you can see the heave of the slab in the middle as a result of the punching of the columns. So this sort of deformation was observed in the vicinity of structures, and in particular some heavier structures. This didn't tend to happen for lighter structures, and it didn't happen in the free field. There was no free field ground failure observed in this case. Then we move also to 99. This is an Adipazari. There were a number of structures that exhibited significant tilt, like the ones shown in these photos, and they tended to have a fairly high aspect ratio. So they were tall relative to the base width. Therefore, there was a significant amount of bending moment imposed on the foundations of these structures, and it resulted in failure of the ground beneath the structure in these tilts. And then this is from the Tohoku earthquake in 2011, where we see that there was a site with about 30 centimeters of free field ground settlement. I don't know if you can see this. Let me turn on the laser. There we go. So 30 centimeters of free field settlement here, which you can measure with respect to this pile supported structure that didn't settle. And then there's a building next to it that was not pile supported, and it settled 70 centimeters. So there was 30 centimeters of free field settlement, and the structure settled 40 centimeters relative to the free field soil. So there was clearly some soil structure interaction effects there, where the structure was sort of pushing itself down into the ground as a result of liquefaction of the soil. So let's talk a little bit about traditional procedures for evaluating ground failure. They're based on, the equation here is the classic CSR, cyclic stress ratio equation, where the demand parameter is the horizontal acceleration at the ground surface. And specifically, this is the acceleration that would exist in the absence of liquefaction. We don't try and account for the effects of liquefaction on assigning the demand to assess whether liquefaction will occur. And inherently, this is assuming free field vertical wave propagation. And so you get shear stresses on horizontal and vertical planes, but in an elastic medium with no plasticity happening, no pore pressure buildup, you don't get a change in horizontal or vertical pressure as a result of those vertically propagating shear waves. So the demand is entirely based on free field, level ground, vertical propagation of shear waves. And then there's cyclic resistance, right? For sand-like soil, we would compute a cyclic resistance ratio with the subscript M, meaning that's for some reference number of cycles, generally for magnitude 7.5 earthquake. And then we correct for magnitude by multiplying by magnitude scaling factor, a K sigma, which accounts for the effects of overburden pressure on cyclic resistance, and then K alpha, which accounts for the influence of static shear stress on cyclic resistance. I'm going to recast K alpha later in this presentation to say that it actually accounts for both changes in demand and capacity. And I'll separate those out once we go to the invariant space. And then, of course, for clay-like soil, we can do a similar analysis, but instead of using a cyclic resistance ratio, we'll use something like tau cyclic over SU for some reference number of cycles, and also 1 atmosphere confining pressure, and for alpha equals 0, and then multiply by some correction factors to get the cyclic resistance of the clay. But what's missing here, right? This is free field only. Of course, what's missing is that there are stresses induced by footings or any kind of shallow foundation or deep foundations for that matter, but I'll stick to shallow foundations today. And there's a couple of things that happen, right? If we look at a point down here below the ground surface beneath the footing, first of all, there's some static stresses imposed by the footing. So maybe, P, M, and V, these are the axial load, moment, and shear imposed on the footing. And they consist of 2 different components. One is the static part, so what loads exist prior to shaking, and then the dynamic part, where there would be some increments of these forces. Okay, and generally, generally there would be some initial axial load but maybe not an initial moment or shear. And then during shaking, we would get the moment and shear, although there could be initial moments and shears too. So the initial stresses will cause a consolidation condition beneath the footing that is anisotropic. It's not going to be a K-naught consolidation condition anymore. There may be horizontal strains, complicated vertical and horizontal stresses and shear stresses occurring during consolidation. So the K alpha effect becomes pretty important now, more important than for level ground conditions. And then, of course, there's the increment of loading that comes from the footing as well. So the footing does tend to increase sigma v prime. So if we look at the CSR expression, right, the bottom part of this expression is going up, which would tend to reduce CSR. But of course, it also increases demand, which here is represented by the sigma v Amax term. So it increases the numerator and the denominator, and it's not clear ahead of time whether there would be a net benefit or net detriment. Some of it depends on the structural properties, right? How much base shear do you get? Is it going to de-amplify motion or amplify motion? Things like that. Okay, so some of the recent work on this has looked into all of the deformation mechanisms that contribute to structural settlement as a result of liquefaction. Most of the recent work is focused on liquefaction, but I think that it's general enough that some of this could be applied to cyclic softening of clay-like soil as well. So this is some work, a figure from Bray and Dashty from their paper in 2014. And, you know, some mechanisms of deformation include ejecta. So sand that used to be underneath a structure might flow up to the ground surface, and that induces settlement in the structure. It may weaken. You get this punching failure where the structure just kind of pushes down. And maybe this is similar to what happened for that site in Tohoku. Maybe there was some ejecta too. And then there's this SSI ratcheting shown by these two figures where the structure kind of oscillates back and forth and works its way down into the ground. And that's basically a shear deformation mechanism. And then there's the sedimentation settlement. Sedimentation would happen with RU equals 1 as the sand particles had maybe initially lost some contact and they settle back down, and then consolidation as water flows out. So usually we would only analyze this sort of consolidation settlement, maybe sedimentation and consolidation based on laboratory tests of simple shear or triaxial specimens to empirically predict free field settlement. But, you know, our typical settlement analyses don't include these other features of behavior that might be the dominant features controlling structural settlement. So what some of the recent research groups have done is numerical modeling, right? So nonlinear dynamic effective stress, time history analyses like the one shown here by Bray and Macedo. And they use advanced constitutive models capable of modeling liquefaction behavior, and then shake these models with a suite of many ground motions, right? Using high performance computing clusters and so forth. So this is a plane strain model. This would model a strip building instead of a three-dimensional building. And after running all those simulations, they will regress for the structural settlement. So DS is structural settlement here, and it depends on axial load, some other parameters that are related to the soil, the thickness of the liquefiable zone, footing width, and then some intensity measures. So this is cumulative absolute velocity and spectral acceleration at the first mode frequency of the structure. And so these are equations now that are fairly simple to use, and they allow us to predict settlement in a way that is more robust than that kind of free field vertical strain analysis that engineers have often used to compute settlements. This is another one by Bullock et al. From Shaded Dashty's group, and they've done three-dimensional analyses. So this is computationally pretty expensive. They've made good use of high performance computing clusters to get this work completed, and a lot of parameter sensitivity studies with various soil layers. And then they would do regression similar to what Macedo and Bray had done to get the numerical settlement as a function of some factors that depend on soil properties, layer thicknesses, and so forth. And then CAV is the cumulative absolute velocity, I think, of the input motion. And then they took it a step further and said, okay, that's good, but these numerical models don't capture all of the features that may contribute to settlement, right? You can't capture sand boils, for example, in a continuum model. It's also pretty widely known that the constitutive models that we use for liquefaction underpredict post-liquefaction volumetric strain, right? There's some nonlinearity in that volumetric strain, whereas the models we use tend to have elastic reconsolidation and they underpredict that settlement. So they have this adjustment factor based on field observations. So this is a nice model that combines numerical methods with field observations to make kind of a semi-empirical prediction of structural settlement. All right, so now moving on to the motivation for this work, right? We already have these methods to do structural settlement. Why do we need another method? Well, I'm going to basically argue that we do need an extension of current liquefaction triggering evaluation procedures. So those current procedures ignore SSI. What I'm going to propose today is a fairly simplified method for including SSI together with the free field vertically propagating shear waves. And so that's the motivation. Some of the numerical methods are, really wonderful, but you should only use them if your particular structure and soil conditions lie within the range of validation of those models. And in order to analyze cases that may differ from those, we need other procedures like this extension that I'm going to talk about today. So here's some of the assumptions that I'm making, and I will acknowledge from the outset that there are some assumptions here that may seem like, how can you be assuming this? And let me just talk through the assumptions and then explain a little bit about our motivation for making these assumptions. So first, we're going to assume that the loading consists of free field shaking involving vertically propagating shear waves. Okay, in reality, I recognize that ground motion is more complicated than that. You get inclined body waves, you get surface waves, there's P waves, there's all kinds of things that happen, but we're going to stick to vertically propagating shear waves in this analysis. Next, we're going to model the soil as an elastic isotropic half space with a mass density rho, shear wave velocity, shear modulus, and Poisson's ratio for static and dynamic loading conditions that are all constant. Now, I am not arguing that liquefaction is a linear elastic problem. It is by definition not linear elastic. It involves nonlinearity. It involves significant nonlinearity. But what I'm doing is trying to extend existing methods for liquefaction triggering evaluation, and those methods are based on a lot of elastic theory. So that R sub D factor that we use when we adjust with depth for CSR is based on total stress, maybe equivalent linear or maybe nonlinear, but time series analyses that do not include the effects of liquefaction, right? So the demand is formulated for a condition that does not have liquefaction, and then it's compared with the capacity. So I'm making the elastic isotropic assumption to facilitate closed form equations for stress at a point, and then comparing those demands with the capacity. I'm not making a claim that those demands will actually be the right demands that exist in real life, just like we don't make the argument that the ground motion we put into a free field liquefaction analysis is the right ground motion that would exist in real life if the soil liquefies. It's a demand parameter. All right, and then I'm going to model the footing as a flexible strip. It'll consist of initial loads P naught, V naught, and M naught, and then dynamic loads delta P, delta V, and delta M. And finally, I'm going to assume that the loading frequency is low enough that static solutions are reasonably accurate. Okay, in reality, when a footing is vibrating, it's propagating waves into the soil. And for example, if we're looking at this point right here, if the wavelength of the waves being propagated from the footing is short relative to the propagation distance, then this assumption 4 is violated. And the phasing of the free field waves with the SSI stresses is more complicated. But it turns out that for a lot of footings, we're interested in points that are pretty close to the footing. And this assumption of a static solution is pretty reasonable. So I acknowledge that footings induce dynamic stresses, right? Not static stresses, but I'm going to use static solutions here. All right, so having laid all that out, we can now formulate equations for the static stresses that exist in the ground. First, the vertical stress component, sigma ZZ naught, has a rho GZ. Actually, there should be a plus Z naught there. There's some initial effective stress at the bottom of the footing elevation. But anyway, this is the self-weight of the soil at that particular depth. And then these terms are all of the SSI stresses. And so usually we'll only have a P naught, typically V naught, and M naught are 0. But anyway, this would allow us to compute the vertical stress at any point. Then similarly, this equation is for the horizontal stress. I'll point out that these are all formulated as total stresses. So these first two terms are computing the horizontal total stress by using a K naught term. But of course, K naught can only be applied to effective stresses. So we have to compute first the vertical effective stress, then add back in the pore pressure to get the horizontal total stress. And then we have the SSI horizontal stresses. And then we would have the shear stress components as well. And there's no shear stress component in this case because I am assuming level ground, right? There's a footing that's inducing shear stress, but there's no self-weight induced shear stress in this case. And then we can compute the horizontal pressure in the out of plane direction. There's a typo, that should be the static Poisson's ratio. So, one thing I didn't point out too, we need different Poisson's ratios for static and for dynamic loading because generally static loading is drained. So I'm making the assumption that maybe the footing induced some excess pore pressure, but all of that excess pore pressure dissipated. And so our static Poisson ratio might be 0.3 or something like that. Whereas in general, when dynamic loading happens, that's an undrained loading condition, and the dynamic Poisson ratio is therefore 1/2 or close to 1/2, maybe not totally 1/2. So anyway, that's why we have different Poisson's ratios. Then the dynamic stresses are very similar. We would only have the SSI components now for the vertical pressure and the horizontal pressure. And now for the shear stress, there's an additional component that comes from the self-weight. So UG0 double dot is the surface acceleration amplitude. And we would multiply by rho Z times R sub D, where R sub D is the typical depth reduction factor that we would use for a free field liquefaction triggering evaluation procedure. So one thing that you will notice is that if we remove the footing completely and set all of these P naught, delta P, and so forth, all of those terms to 0, we would recover the traditional free field evaluation procedure. So I wanted to formulate it in a way that works for the free field and then extends it. So what we would do then after computing these stresses is formulate the Cauchy stress tensor. And we're doing plane strain, so some of these terms are 0, in particular shear stresses involving the Y component. And so we get the, the normal stresses in horizontal and vertical directions, and then the shear stresses in the XZ plane. Of course, you could take this method and extend it to 3-dimensional loading conditions too. It's just that the equations for computing the stresses would be a little bit more complicated and would depend on the footing length in addition to its width. All right, so after getting that stress tensor, I take its eigenvalues, and that gives me the principal stresses, and then can compute the deviatoric stress invariant Q and the mean effective stress P naught prime, right? So I'm going to do P naught prime because this is going to be related to both the definition of CSR, where sigma V prime appears in the bottom of that expression, and also for setting the initial shear strength for clay, right? So the undrained strength of clay depends on consolidation pressure. And that's just the trace of the effective stress tensor. All right, now here's one of the key concepts in this method. This is where I'm going to take the traditional cyclic stress ratio equation, and I'm going to represent it in a simpler form, just RE times tau cyclic over sigma V naught prime, where tau cyclic is equal to the sigma V naught A max over G times R sub D term. And I'm going to cast this cyclic stress ratio in terms of the deviatoric stress invariant and the mean effective stress instead. And the reason I'm doing that is that it makes it general enough that we can apply it for any stress path. We're not constrained anymore to a simple shear stress path. Although if we do happen to have a simple shear stress path, this CSRQ, which is the deviatoric cyclic stress ratio, will be the same as CSR. Okay, so it's pretty straightforward to do this. First, I define Q naught. That's the deviatoric stress invariant under K naught consolidation conditions that exist prior to shaking for free field conditions. And then, so basically what I'm doing is taking the free field case, so no structure right now, and figuring out what the CSR equivalent is in terms of invariance, right? So here's the Q naught for free field. Here's Q, where I've left out some steps here, but if you compute the Cauchy stress tensor, calculate the deviatoric stress invariant, you would be able to represent it this way. It's the square root of Q naught squared plus 3 times tau cyclic squared, where tau cyclic is just that term right there. So what we can do is invert this and see that tau cyclic is equal to Q squared minus Q naught squared over 3 and plug that in up here. Then P naught prime is sigma V naught prime times 1 plus 2 K naught over 3. We can now solve for sigma V naught in terms of P naught prime and plug it in here. And we end up with our equation for CSRQ, right? So this is identical for free field loading condition to the definition of CSR, but it's cast in terms of invariance instead of shear stress on horizontal and vertical planes and vertical effective stress. It's using deviatoric stress invariance and mean effective stress instead. All right, and the benefit is now we can compute Q and Q naught and P naught prime for any kind of complicated stress path, not just for one-dimensional loading conditions. So it's a generalization of the traditional CSR equation. All right, so that's the demand side. I'm going to talk a little bit about the capacity side too. Let me grab my clock. I want to make sure I'm sticking to the time here. All right, so this is going to first be the K alpha correction. So K alpha is a correction that we apply to account for the influence of static shear stress on liquefaction resistance or cyclic softening resistance. And it's usually been conceived purely as kind of a capacity term. And so the way that these are derived is usually using a simple shear device. We consolidate, oppose some static shear during consolidation, and then we put some cyclic shear on top of that and look at how that influences the soil strength. So here's a couple of K alpha relationships. What we see for sand is that for loose sand, K alpha tends to decrease the strength or the capacity throughout the range of alpha values. Alpha is equal to tau static over sigma V prime. Whereas for denser sands, it may increase it. And, you know, if you kept increasing this, it would have to eventually come back down because you'd have a static failure at some point. And then the same thing for clays here from Boulanger and Idris shows that K alpha tends to decrease regardless of OCR. So here's two lines, one's for OCR 1 and 4, and you just get this reduction in cyclic strength as tau cyclic over SU increases. So let's talk a little bit about what K alpha is in the context of this new CSRQ idea. So K alpha, as I said, was originally developed from simple shear tests with a static shear stress on horizontal and vertical planes. So here's an example, right? We have 100 kPa vertically, 50 kPa horizontal, so K naught is a half, and we have 0 static shear stress. So what would be alpha in this case? Well, it's 0, right? There's 0 shear stress on horizontal and vertical planes. Therefore, we would say this is an alpha equals 0 consolidation condition, and we can then impose cyclic shear stress on top of that maybe and get a alpha equals 0 strength for this soil. All right, well, what about this one? We have 100 kPa vertical, 50 kPa horizontal, and now 20 kPa shear stress, static shear stress imposed. And so I have let's conduct a poll here, but I can't see any of you. I can only see my screen, so I don't feel like we can do an interactive experience. But maybe you could answer in your head, like what is alpha in this case, right? We have 20 kPa with 100 kPa vertical. Well, alpha is just equal to 20 divided by 100, so it's 0.2 in that case. Pretty easy, right? And now if we did a shear test on that, we could see if it's stronger than this one and devise the K alpha for the 0.2. All right, let's look at one that's a little more complicated. Let's say that I rotate the element now, and we have 107 kPa in this sort of oblique direction and 43 kPa in an orthogonal direction and 0 kPa of shear stress. So what is alpha for this one? Well, I'm not sure because alpha is formulated for horizontal and vertical planes, right? So usually we're looking at what is the horizontal vertical shear stress. But, you know, if we kind of rotate our heads, maybe this 107 is now the new vertical direction and the 43 is the new horizontal direction, and there's 0 shear stress in those directions. So maybe alpha is equal to 0, right, for that particular case. Well, it turns out that alpha is equal to 2 for this, 0.2 for this case. The way that I got these numbers was simply to compute the principal stresses for this loading condition here and the principal plane orientations. And so these two stress conditions are identical, right? There's absolutely 0 difference between this stress condition and this stress condition. Yet the shear stress is 0 on these planes, but it still is alpha equals 0.2. All right, so that's a little bit of a complicated factor. Okay, K alpha accounts really for 2 things, right? What is the stress on the soil? How much shear stress is there initially, and how close to failure are you starting? And then it also accounts for fabric. So by rotating the element, you know, maybe the fabric is changing because the soil is anisotropic and the alpha effect may be different. But the stresses themselves, right? This is a stress condition that's identical to this stress condition in some ways because you have 0 shear stress on those planes. But this is still an alpha equals 2. Well, now let's go back to this first one. Given that this one has an alpha that's non-zero, what about this? Is this really alpha equals 0? Certainly if you rotated this element, there would be shear stress on other planes. So I think our definition of K alpha is a little bit too closely tied to simple shear stress path, and we should maybe think about it more in terms of invariance. And I know that that may be a controversial statement because there's a lot of history with dealing with K alpha, the way we've dealt with it. So let's take a look now at what we would get for a direct simple shear stress path in terms of this CSRQ parameter. So if we have this initial condition that has no alpha, right? Tau static equals 0, and we impose a tau cyclic equals 20 kPa on top, we would get CSR is equal to 0.65 times 0.2, right? So 20 kPa divided by 100 kPa, that's tau cyclic over sigma v prime. And then we would multiply by this R sub E factor of, generally it's usually 0.65. So the CSR would be 0.13. Well, CSRQ would also be 0.13 because we formulated it to be exactly the same as a K-naught consolidated direct simple shear stress path. If we go to this one now, where we have a tau cyclic of 20 and we're imposing a tau static of 20 and we impose an additional 20 in cyclic stress, CSR stays the same, right? It's 0.13 because we have 20 kPa of cyclic stress divided by 100 kPa of vertical effective stress. But the CSRQ is higher. It's 0.225. And the reason for that is that our CSRQ definition incorporates Q naught. So it incorporates the initial deviatoric stress invariant, which is bigger for this case than it is for this case. And so we get a difference in CSRQ. So what that tells me is that this new invariant-based method actually includes a K alpha component already, right? It's adjusting the demand. K alpha is both a demand and a capacity parameter, and CSRQ is giving you a higher value if you have a higher initial static shear stress. So one thing I've done, if we come back to this clay, and as a preview, the centrifuge modeling will involve clay. If we reformulate these test results in terms of these 2 different contributions to K alpha, so K alpha D is what I was just talking about. That's the difference in CSRQ that you would get for an alpha equals 0 condition compared to an alpha condition. And it's a fairly simple equation right there. This is implied in the CSRQ formulation. Then you could subtract this out from the lab test data and you'd be left with a capacity ratio, right? This is K alpha C. So K alpha is equal to K alpha D times K alpha C. And this K alpha C can be fit using a functional form right here. And what we see is that while the clay had a K alpha overall that was decreasing, it has a K alpha C that initially increases and then decreases. So to me, that means that some alpha initially actually increases the capacity due to this fabric anisotropy before it decreases as you reach tau static over SU equals 1. All right, another correction that we need to make is for stress path. So to do that, we can compute the Lode angle. And this is just an invariant that's based on principal stresses. And for direct simple shear stress path, this angle theta is 30 degrees. For triaxial extension, it's 60. And for triaxial compression, it's 0. And of course, this equation, if you solve it, is only going to return theta between 0 and 60 degrees. But if you define theta, it could be anywhere in 0 to 360. So this is what the resulting strength envelope looks like. And you can set the C parameter, which is the ratio of, let's see, this is the direct simple shear strength divided by the triaxial compression strength, right? So if we set a number of equal to 2/3, you would get a strength envelope that looks like this blue line, or a KP, K path correction, that looks like that blue line. So you get a higher strength here, lower strength for direct simple shear, and then lower strength yet for triaxial extension. Or you could set C equal to 1, and then this is just a circle. The strength does not depend on stress path at all. We're going to use more like this blue line because that accords better with observations of strengths of clay. Okay, now for the magnitude scaling factor. We have not formulated magnitude scaling factor expressions that are simplified that people can use in an analysis like the way that we do for traditional liquefaction evaluation. But we do have reason to believe that magnitude scaling factor is different when you have structural loading than it is in the free field. And what I'm showing here is kind of a preview for something I'll talk about later. This bottom one is basically a free field analysis, right? So this is the a demand measure for free field loading. And this is the same demand measure beneath the structure. And I haven't talked about how I got these quantities yet, but basically we've got an equivalent number of loading cycles of 42 for the free field and 78 for beneath the structure. And this makes sense to me because, a structure is going to have its own dynamic response, and it may impose a large number of cycles on the soil, much larger than you would get in the free field. So I think probably in general, magnitude scaling factors are going to be different and they will be smaller. A lower magnitude scaling factor reduces the capacity more. So that would be, for a given number of cycles, a lower magnitude scale factor. All right, so the resistance equations now are given here for sand-like soil. We have just the same equation we had before, except instead of K alpha, we have K alpha C. The K alpha D is actually embedded in the CSRQ, so we don't need to add it to the capacity. And then there's a path correction. That would be for sand-like soil, where CRRM is just the typical cyclic resistance for 15 cycles. It's based on relative density. Then for clay-like, we have the same thing where we have this magnitude scale factor, K alpha C, and a path correction there as well. And I'm also going to impose a rate correction because we know that clay, the undrained strength ratio of clay should be rate compatible. So let's move on to the centrifuge modeling. And this will go by pretty quickly. Don't have a huge number of slides left, which is good because we're almost at the end of the hour. This is a sketch showing the centrifuge models we conducted. One of them had a layer of clay that was fairly thick, and we consolidated the clay from slurry on a hydraulic press and then put it in the centrifuge models. And it was close to being normally consolidated, maybe just lightly over consolidated once we spun up the centrifuge. And then we had another one. We had some problems with consolidation time for this clay layers. So for the second test, we put some sand layers in the middle. And also, you know, clay layers in the field generally do have interbedded sand layers. So this may be a more realistic stratigraphy anyway. We put the same structures on this model as well. So we had one structure that's kind of like a single degree of freedom oscillator. It's an I-beam with a steel plate mounted to the top. And then we had these other kind of portal frame structures that are each just, you know, 2 columns with a mass across the top. And the footings were pretty close to the top of the top layer of clay here in this case. The natural frequencies are different. This shorter structure has a shorter natural period, being stiffer. Then we did simple shear tests on our clay to quantify the cyclic strength. So we did blends of bentonite with non-plastic silt, and that's shown here in the blue line. This is what we used for the first test, JZB01. And then we had a second blend that was a kaolinite blend with non-plastic silt. So it's 78% silt, 22% kaolinite. For the bentonite one, it's 95% silt, 5% bentonite. And in both cases, the PIs are fairly low, right? 9 and 14. So this is kind of in the range where we would say these are clay-like soils. These are not soils that for which we would do a traditional liquefaction triggering evaluation. So it's definitely a cyclic softening sort of thing. And then we have a static shear strength factor that is right here where we oppose that rate correction. Here's the structure properties. So these are prototype units. The structure 1 is that single degree of freedom oscillator, and it has a fixed base natural frequency around 1 hertz. Flexible base is a little lower, lengthens a little bit. Then the other structures, you know, that shorter structure was around a 5 hertz natural frequency fixed base, or 2.3 flexible base, which we got from measurements of vibrations during centrifuge spinning. And then the taller portal frame structure had a 2.3 hertz fixed base frequency, or about 1.5 hertz flexible base. And these frequencies all go down a little bit for the second test because we spun the centrifuge to a higher level of 57G instead of 40G. Then these are the base motions that we imposed. So we took some recorded ground motions. This one, TCU, was a motion recorded from the Chi-Chi earthquake. And then we also used motion from the Port Island Array in Kobe, and imposed motions with a range of intensities on the base of the model. And this is for the first model, and this is for the second model down here. And here's some example response parameters. So this is, let's see, acceleration at the base of the model. This is the free field acceleration. So there was amplification for this particular motion between the base of the model and the free field ground surface. And then here's the top of structure 1. So pretty big de-amplification here. And the reason is simply that the input motion frequency content was pretty high relative to the natural frequency of structure 1. So we were on the sort of the descending branch of the transfer function for that structure, and we got lower accelerations at the top. We can now compute the components delta V and delta M based on the measurements from the centrifuge model. So these are what we used as an input to our cyclic softening analysis, and we did the CSRQ calculations at every time step based on the measured delta V and delta M, and then delta P was 0. And here's the rotation. So we do see some permanent rotation building up. This one had over 2 degrees of rotation due to shaking. And this structure ultimately did tip over. So it kind of progressively accumulated some rotation with each shake and eventually failed in between motions. It didn't fail dynamically, it failed statically. And then this is the settlement. So you see it going up to about 10 centimeters during this shaking event. So after taking those input quantities, right, we can compute some fields at every point and then create these contour plots. So this is a field showing P naught, right, the initial mean stress. Q naught is the initial stress deviator. And then Q is during shaking at a particular point in time, right? So I took a snapshot in time and produced this plot. And so you can see that there's higher loading beneath the footing and less loading in the free field. So it is significantly different. And then this is if we calculate the CSRQ, but take out the effects for this tau cyclic over SUQ is removing the effects of K alpha and magnitude scaling factor and so forth. So basically, this is the kind of quantity you would compare with the cyclic strength in order to compute a factor of safety. And you see a big increase beneath one side of the footing and a corresponding decrease beneath the other side because the footing was rotating in a certain way that actually unloaded here and loaded there. Of course, over time, it will rotate back, it'll go back and forth and you get stress reversals. So if we do a cycle counting procedure, right, this is the figure I showed before, we can identify these peaks and count up the number of loading cycles and then compute a magnitude scaling factor basically from this. And we can do that also in the free field. And then we can produce a plot like this. This is the CSRQ for a magnitude basically for 30 loading cycles, right? And so we have something that's much more symmetric, although it's not perfectly symmetric. We have a little bit higher CSRQ on the left side because the ground motion was asymmetric in this case. And so when you integrate this over all of the loading cycles, you do get a slightly higher load on one side than the other. And then here's the factor of safety. And what we see in the free field is the factor of safety is fairly high at the surface since the clay was more over consolidated there. And then it decreases and it does go a little bit below 1 in the free field when you get to the bottom of the clay, but it's significantly below 1 beneath the footing, right? So if we did a free field analysis in this case and ignored the stresses from the footing, we would not do a good job of predicting this failure. And again, this structure did tip over. This is all for structure 1. So then if we repeat that calculation for all of our footings for every motion and compute the average factor of safety. So all I'm doing is taking the average factor of safety along a line right here. And this is the full thickness of the clay for the structure 1 for test 1. For the second test, we only averaged over the top clay layer instead. So there's some judgment involved here in getting this overall metric. But this is the average factor of safety versus the observed dimensionless settlement, S over 2B, where 2B is the full width of the footing. So what we see is there's not a lot of settlement as long as this factor of safety is higher than 1, which is for the smaller motions. And then as the factor of safety drops below 1, we start to see this increase in the amount of settlement. So the predictions track pretty well with what was observed in that our factor of safety is less than 1, or what were associated with the more significant settlements. On the other hand, if we do a free field analysis, so we can, in our method, just set x equals infinity, and that puts the stress point really far away from the footing, and that's a free field analysis case. We get much higher factors of safety, and we see that there's significant structural settlement, even at factors of safety as high as between, up to 1.5, even at 2, there's some significant amount of settlement occurring here. And we only had a few points that actually had a factor of safety less than 1. So ignoring the effects of structural interaction on the soil would be unconservative in this case. All right, so I'm kind of wrapping up now, right on time. So we have this method to include SSI effects in a method that's basically an extension of existing liquefaction triggering evaluation procedures. We do that using stress invariance, which is a little bit more complicated than just using horizontal and vertical stresses, but also more robust and correct when we have complicated stress paths. The CSRQ idea is a new idea. It's equivalent to CSR for free field, but it allows us to compute cyclic stress ratio for complicated stress paths beneath footings. And then I also talked about invariant-based adjustments for path and static shear stress. And we have some future work left to do to formulate magnitude scaling factor expressions for loads beneath structures. So we applied the approach to some centrifuge models involving strip footings resting on clay. And the factor of safety from the proposed model tracked pretty well with observed settlements and rotations. We don't have a model yet to say if your average factor of safety is this, your settlement will be that. I think that we only have this for one centrifuge model, so there's plenty of work left to do to sort of empirically validate it with field case histories to develop a more robust recommendation. But we do know that factors of safety based on free field shaking intensity would underpredict ground failure potential for these centrifuge models. So I'm going to acknowledge the National Science Foundation. They provided the funding to do this work at UC Davis, and also thank Jason and John again, and I will stop there, and I'm happy to answer questions if there are some.
Thank you, Scott. This is very interesting presentation. I didn't have the chance to look at that yet before today, so it's really nice to see. It was really nice to see it today. So I'm asking to the floor is there is any question? You can just use the tool to raise your hand if you have some. In the meantime, I have a question for you. You mentioned in the conclusions that basically there is still work to do to define like a framework and a method to define all these, to define the whole method, let's say. So are you planning to have, together with empirical models, to empirical data, some numerical modeling? Because you mentioned that we have now, as you mentioned, we have the high performance computing facilities and the opportunity to run a lot of numerical analysis. So are you planning to do something like that?
I don't have plans to run numerical models now, but I think what might be useful, I know that Shide has published a lot of her numerical models on design safe. So they're all up there, you know, using, I think those are all really high quality pieces of work. So it would be interesting to take her numerical models and compute these factors of safety and see if that has predictive power in terms of the settlements that were predicted from hers. I think that, I don't know if Jorge Macedo and John Bray have published their numerical models as well, but there's plenty of existing work out there. It's all on sand though, so I think there is room to do the same for clay-like soils. Might also have cyclic softening and settlements and rotations and so forth.
Thank you. We have a question from Gianluca. Gianluca, please go ahead.
Hello, can you hear me?
Yes. Yeah, thanks, Gianluca.
First of all, thank you for the presentation. And actually have two quick questions for you. And the first one is actually on the very last slide that you showed, or in the conclusion, you said that this method works well with real case histories. So it seems that this new methodology that you proposed seems to work well compared to real case histories where classical CSR methods failed. So if all of the case history actually matches this new methodology, I don't think that the assumptions that you made, that you said that they were strong assumptions, I think that could be strictly valid in those cases, because if based on the scientific method, if the observation validates the theory, the assumptions that you made, despite being strong, they could actually be supported really well. Do you think that this is the correct approach in saying that some hypotheses may be strong, but it doesn't matter that they're strong if the final observation actually validates the theory?
Yeah, I agree with you about that point for sure. Any kind of model we use, regardless of how complicated it is going to still have some deficiencies, right? There's never such a thing as a perfect model. The only issue I would say is that my conclusions were not based on field observations. I was limiting my observations just to the centrifuge model results. So I don't really know yet how well this works for field case histories. I think that there's additional work there for sure to go and get some of these field case histories and evaluate them to see, like for example, if we could analyze the structure from the Chichi, Taiwan earthquake that had the shallow foundation failures and no free field failure and predict both of those things correctly, that would show some power in the method, despite, like you said, despite the assumptions that are admittedly pretty simplifying, right, of the real problem.
Yes, and another question actually is if you could elaborate more on why the magnitude scaling factor should be a lot different compared to the classical one, because I think that I didn't fully understand that concept. If you could.
Yeah, sure. So First, the magnitude scaling factors are based on free field loading conditions, and they've been formulated from ground response analyses that do not include the effects of liquefaction. So it's like people will run a site response analysis, count the number of loading cycles that exceed some threshold, and then compute the equivalent number of uniform cycles based on the slope of the CSR versus N curve. You know, there's this whole process that goes into it. Then you get the magnitude scaling factor. The problem with SSI is that you've got the free field shaking demand. So there's some stresses exerted on the soil from that. But then there's another increment that comes from the structure vibrating back and forth. And let's say we have a linear elastic structure with 5% damping. It's going to kind of ring around a lot, right? It may vibrate a lot back and forth and induce more stress cycles on the soil, even for the same input motion. So usually we would say like a magnitude 7.5 earthquake is associated with 15 cycles of loading for sand and maybe 30 for clay. And that has to do with the different slopes of the sort of the cyclic resistance of those soils. Well, with a structure, those numbers may go up quite a bit, right? And it would depend on some factors like how much influence does the structure have on the stress at a particular point? Is it more dominated by free field, in which case I think the traditional magnitude scaling factors are fine? Or is it really heavily influenced by stresses from the structure? And is the number of structural loading cycles higher than or less than the number of free field loading cycles? So I don't know. I think magnitude scaling factors will go down, which would tend to reduce our resistance as a result of the increased number of structural loading cycles. But it's also possible that they could go up if you had a structure that just didn't have that many loading cycles, like a really long period structure may not have that many loading cycles, for example.
Yes, understand. Yeah, thank you.
All right, sure. Thanks for your questions.
Okay, we passed the hour. I just want to share again my screen just to announce that Housecut was saying the next speaker will be John Stewart from University of California, Los Angeles. The presentation will be on April 13 at 5 p.m. And the title of the presentation is Seismic Pressure Retaining Walls Based on Soil Structure Interaction Principles. So more detail, you can find more details on the website of the event. And I guess that we can stop it here for today. I thank everyone for being here, particularly Scott for taking the time to give the presentation. He's been great as always talking with you and listening to your research. So I hope to see you all next time. Have a good day. Bye. Bye everyone. Thank you.